Okay, welcome back. Hope you had a good break. So I'm going to talk about some work in Google Brain. And let me just dive into it. So everybody can hear me and see me okay. I think it should be, settings should be the same. Great. So Google Brain is part of Google Research. It didn't always start out as part of Google Research. It started out as a project in X, which is sort of part of Google doing exploratory work. It was founded in 2011, so 11 years ago. And the mission of Google Brain is, the stated mission is to make machines intelligent and improve people's lives through advancement in the fundamental theory and understanding of machine learning and through research in the service of products. So it's very deeply integrated into Google. It's a really interesting place, I would say. I mean, I could spend a whole hour talking about that, but why don't I talk about some of the research that we do? So just a little bit more about Brain as part of the research organization. So it's quite globally distributed. There is a center of mass. You can't see a center of mass here, but like the rest of Google, there is a team in Mountain View in California that is really in the middle of Google headquarters. It's not kind of off to the side of Google. It's actually like right next door to the CEO's office or something like that. But the Brain organization is pretty distributed globally. Just a couple of days ago, we announced our Sydney office. We have a small presence in London, a big presence in Zurich and Paris, Berlin. We started an office in Accra in Africa, in Ghana, etc. So the history of Google Brain is really interesting. A lot of quite disruptive innovations in machine learning were contributed to by Google Brain. Things like Disbelief, the first distributed system for training neural networks, the first deep learning models in production at Google, doing acoustic modeling. The famous sort of CATS paper got a lot of attention kind of in 2012. First kind of very big training of neural networks in a distributed manner. Concepts like word to vec or seek to seek, GoogleNet. Over the first few years of the Brain organization, there were a lot of collaborations with many product teams. So live deep learning experiments in ads, the concept of distillation that's often used in neural networks, rank brain, which is part of how Google search works. Then, there was a realization that we needed frameworks for doing deep learning across the company. So TensorFlow was developed in Google Brain, and there was a collaboration on the hardware side to develop tensor processing units, DPUs, which provide a lot of acceleration for deep learning workflows. JAX is something that I'm going to talk about a little more if I have time, is really a framework that's kind of, at least within the research parts of Google Brain as well as DeepMind, is sort of replacing TensorFlow for us. A lot of excitement. It's an open source project, so there's a lot of excitement there. Work on AutoML transformers, a lot of language models. I would say most of the very large successful language models are now based on transformers, things like BERT, ML for chip design, MUM, LaMDA, POM, Imagine, Party. I'll talk about these last three in a minute. Okay. Brain interacts a lot with the academic community. If you look, there's like an overwhelming number of publications, many very highly cited papers and things like that. So it's really very much engaged with the academic community. There are a lot of collaborations with universities, a lot of presence at conferences and things like that. But it's not just an academic research-oriented organization. There are also a lot of deep collaborations with product teams across all of Google. You know, things like search, YouTube, Assistant, Cloud, etc. So basically all of Google. In fact, you know, Google, as of a few years ago, has really started talking about itself as an AI-first company where research is kind of like the infrastructure for the rest of the company. So I think there's a big difference between places where research is really the foundation of what the company does versus places where research is something off to the side. And if you think about the history of Google, I mean, it was founded by kind of two PhD students, right? And so they've always been, the company's always been engaging with researchers and academics. There are a few exciting trends in machine learning in particular that Brain has been sort of involved in. More capable general purpose machine learning models, looking at major improvements in efficiency in ML models, trying to develop more personal and societally beneficial machine learning, then trying to grow the impact in engineering, science, health, sustainability, and really trying to understand these systems. So I'm going to skip over these so that I can talk about some of the research project overviews. Okay, so let me dive into these things. There's a lot of projects. I'm selecting a few of them. These, I mean, this is just a few that I had in a larger deck. I'm going to select a few of them. So, so let's talk about a fun one. This is text-to-image generation models. And we recently released two models, one called Imagine and one called Party. They're actually two different approaches to solving essentially the same problem, which is given a text query, have the computer generate an image, okay? Remember, research is not about products necessarily, right? So when I present research, it's important to realize that really this is research. And so it's actually often not clear to us what the product use is going to be, right? And in fact, sometimes it's like there's a big gap between having a research breakthrough and really figuring out what's a safe, useful product that people might want to interact with. Okay. So Imagine is basically a text-to-image model that can generate photorealistic images, and it's based on a concept called diffusion. So diffusion models are interesting. I quite like diffusion models because I like probabilistic models. And so anytime the deep learning community kind of gets like taken over by some very probabilistic concept, I feel like a little bit of excitement. So a diffusion model is basically a generative model where you can think of starting from the data. If you apply noise to the data in multiple steps, that's like a random walk or a diffusion, and eventually you get to random noise. And that process, when you run it backwards, becomes a generative model. So the generative model starts with random noise, and then it looks at kind of developing a stochastic process that goes from that random noise to data points. And it's basically guided, that stochastic process is guided by a neural network with tunable parameters, and the generative model tunes those parameters to be able to generate the data. Very much like a VAE, if you think of a VAE, it goes from random noise as well to generating data. Okay, so here's some just technical details. of the model in Imagine. The input is text. You give it a text string or sentence. The output is a fairly high dimensional input, image, 1,000 by 1,000 pixels. And the way it does that is interesting. It's hard to go straight from the text to the 1,000 by 1,000 image. So what you do is you go from the text to a small image, 64 by 64. And then you condition on that, and you go again from the text and a 64 image to a higher dimensional image, 256 by 256. And then finally from 256 to 1,000 by 1,000. Okay, and because at every stage you're conditioning on the text, the first thing can be crude and sort of not great at representing what's in the text, but the text keeps coming in and trying to make sure that the elements that are in the text are actually in the image as well. The diffusion process takes about 16 seconds on a TPU to generate 8 samples of images. And we often just we'll take the 8 samples and we look at them, and sometimes we cherry pick one out of the 8 that looks particularly nice and we show it to you. So clearly, there's we could show 8 examples of everything, but it would be pretty boring. It's, sometimes we'll show a couple, sometimes we'll show 2. Often, in my experience playing with it, the 8 samples are all pretty good, right? They're not way off, right? Some of them are just a little better than others. One of the interesting things about Imagine is that it uses a frozen language model. So this is a great kind of trend within deep learning, which is you train a model. And actually, if you study statistics, you can think of models as compact representations of data sets. Okay, that's kind of what a model is. It's another way of thinking about it. You train a model, and then you take that model and you reuse it for many, many purposes. So it might be expensive to train the model, but actually once you have it, using and executing on the model could be quite cheap. And so it's great that we can reuse these things. And of course, there are many organizations that are also contributing open models out there. And I'll just be upfront. We do open source a lot of things, but we don't always release models because there are a lot of ways of misusing these models. And I think as Google, as a company, we need to be very careful about people going and misusing our models for various reasons. Whereas some, other organizations, academia, startups, I mean, maybe they don't worry about that as much, but we tend to worry about that a lot. We can plug a different language model in there, and we anticipate getting even better results. So here's kind of how it works. You give it a query, a photo of a group of teddy bears eating pizza in Times Square. Before Imagine, I don't think, or before this whole text to image thing, I don't think that image was actually anywhere on the web. So it's not like it's picking the nearest sample of images out there. There's a frozen text encoder. It creates an embedding. That embedding and some random noise goes into the diffusion model. It's conditioned on that embedding. And then the diffusion model runs and it generates an image. The 64 by 64 image then goes in here, generates 256 by 256. And then that goes in and generates 1,024 by 1,024. So many of you are familiar with DALL-E and DALL-E 2. And we can do comparisons. And it's sort of a race. Currently, both Imagine and Party that I'm talking about are generating better samples than DALL-E 2. But give it a few months. I'm sure somebody else will come out with something that will be maybe even better. So you can see some compositional thinking, like a yellow book and a red vase. 3 out of 4 of these are good. This one, I'm not sure if the book is yellow. It's hard to tell, right? The wall is yellow. So it's not always getting things right. A blue dog. Blue dogs are not usually blue, but It can generate a blue dog. If you do comparisons with human raters, you can get sort of some evidence that people seem to prefer Imagine to DALL-E 2. You know, and then there's just some examples of, you know, queries and things. This you've just seen, well, seen a version of this corgi dog with the sushi tray, amigurumi, which I think is this sort of knit thing. I like this one. Aquarium frozen into a popsicle professional photograph. Studio shot of minimal kinetic sculpture made from thin wire shaped like a bird on white background. Lifelike oil painting of a cute kitten with a pearl earring wearing a turban in the style of Vermeer. So it's pretty cool. But diffusion models are not the only way of doing this. So the interesting thing is you could say, machine learning, okay, you have to use diffusion models to do this. Well, you know, we had another team that was exploring a different approach, and this is called PARTI, Pathways Autoregressive Image Model. And PARTI is actually somewhat different. It uses kind of a language modeling approach. So basically, it takes an encoder-decoder autoregressive architecture and treats text to image as machine translation. So it tokenizes everything. And then it kind of translates from the text, like two dogs running in a field. And then this is like the encoder, and then there's a decoder, and then it uses a vision transformer, or VIT, VQ-GAN type architecture to generate the image. So the image is tokenized, image tokens are rasterized, it's flattened. It's kind of a weird thing. Like if, you know, diffusion seems more elegant because it's sort of generating the whole image at once. This is basically kind of going and generating like the rasters of the image, but actually then it makes it all coherent. And I don't know if you can see this well. The interesting thing here is that we can also look at how PARTI does as we change the size of the language model. And so here we have a portrait photo of a kangaroo wearing an orange hoodie and blue sunglasses standing on the grass in front of Sydney Opera House holding a sign on the chest that says, "Welcome, friends." Okay, that's a pretty long query. You know, honestly, like, you know, even 5 years ago, if you told me that a computer could take that and generate an image, I'd be like, nah, you know, there's no way. But it's doing it. It's kind of crazy. But the interesting thing is you can see, you know, it's kind of weird and creepy with its 350 million parameters. It doesn't really quite look like the Sydney Opera House. Once you get to 20 billion parameters, the text comes out correct, "Welcome, friends." It really is a kangaroo wearing blue sunglasses and a hoodie. It really is the Sydney Opera House. Again, you know, if you compare a smaller model to a larger model, it's getting the text right, green sign that says very deep learning, and is at the edge of the Grand Canyon, puffy white clouds are in the sky. Okay. So it kind of gets all that. All right. And, you know, it's much more fun to look at this than boring tables of results, but, you know, we can compare things using various measures of, you know, model generation quality. Some more fun examples. I know it's late in the day. It's nice to have fun pictures to look at. A high contrast photo of a panda riding a horse. The panda is wearing a wizard hat and is reading a book. The horse is standing on a street against a gray concrete wall. Colorful flowers and the word peace are painted on the wall. Green grass grows from cracks in the street. DSLR photograph, daytime lighting. You can just kind of go through that and check all these. We didn't generate 100 images to get that. I mean, this is one of the 8, I think, that was generated. Other ones were pretty much, they were pretty good. Maybe they didn't have all the elements, or maybe there was a little bit confusion, but you know, it does this, it generates this stuff. Here's another one, a photo of a frog reading the newspaper named Today, written on it. There's a frog printed on the newspaper too. A photo of X made of water, where it can be panda, maple leaf, four-leaf clover, dragonfly, and kind of more examples. Okay, so that's Party and Imagine. Let me talk about PaLM, which is a pathways language model. And it uses a concept called chain of thought reasoning or prompting. So as in other examples, we found that scale helps, but scale is going to have its limitations too. I'm going to talk about that in a minute. So PaLM was a language model that there is a once-a-year event called Google I/O, where Google talks about some of its product launches, but also ends up talking about the significant kind of research launches. So we talked about this. So this is Sundar talking about PaLM at the last I/O. It's a large model, 540 billion parameters. It's a dense decoder model. At the time, it was the largest model to date, but I can't keep track because, you know, people develop these things. It's based on the transformer architecture. So I think, you know, it's good if you all study up on transformers if you're interested in particular in language or vision these days. And it's trained on a large multilingual data set. And one of the interesting things about PaLM is to scale up these models. We need to kind of look at even more distributed learning, right? So the TensorFlow, sorry, the TPUs that we have are organized into pods. And this was the first model that we got to train across multiple pods. So that's a way of really scaling up these models to larger training architectures. And it's trained on a lot of tasks. So it ends up actually trained on more than 200 natural language processing tasks. So it's sort of trained and it can sort of generalize across, and it's evaluated across many, many different tasks. And generally, like as we've scaled up these models, we found that they do better on more of these tasks. So this is just a comparison. You've probably seen Gopher and Chinchilla from DeepMind and PaLM. And, you know, there's sort of interesting things. Chinchilla was very interesting as the benchmarks here. There was a very nice paper called the Beyond the Imitation Game, which was a very massive collaboration among many researchers at many institutions, looking at benchmarking of language models. So in this space, like it's important to have these large collaborations because people have to come in with different benchmarks and different views on how to evaluate these things. So you can measure the performance across these benchmarks. Couple of things to note, performance improvements have not yet plateaued. I mean, we imagine they will plateau at some point, right? Because the amount of useful data that you might get is, you know, limited. But they haven't plateaued yet. Chinchilla was very efficient for the number of parameters that it had. PaLM is here, so PaLM performs better, but, you know, I think if we combine some of the ideas of Chinchilla and PaLM, we could even get better efficiency. One of the really interesting things about PaLM was that if you try to give these language models, essentially you train the language model and then you give it a prompt, and sometimes the prompt has examples of what you want it to do, and then you see what it does. So here is the prompt, that's the input. Standard prompting would be something like this. Question, Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? Answer, the answer is 11. You're giving it this as an example, a data point, okay, of what kind of behavior you want. And then you give it another question. Cafeteria has 23 apples. If they use 20 to make lunch and bought 6 more, how many apples do they have? And the model gets it wrong. The answer is 27. That's incorrect, okay? So if you try to jump to an answer, this is just text in, text out. It's just a language model that's trying to predict text. I mean, that's kind of the weird thing about this, right? If you just jump to it, the model gets it wrong. But then if you change the prompt in a particular way, this is called chain of thought prompting. You change it so that your prompt actually tells the model, you know, the steps of linguistic reasoning. It kind of gives it a pattern, an extra bit of information. So the added thing here is Roger started with 5 balls. Okay, that's just restating this. 2 cans of 3 tennis balls each is 6 tennis balls. 5 plus 6 equals 11. The answer is 11. So the answer is the same, but you tell it the steps along the way. And then for that same, you know, question here, the cafeteria had blah, blah, blah. The answer now involves that chain of thought. The cafeteria had 23 apples originally. This is the answer the model gives. They used 20 to make lunch, so they had 23 minus 20 equals 3. They bought 6 more apples, so they have 3 plus 6 equals 9. The answer is 9. Okay, so this is pretty interesting. This is pretty cool, and this is very cheap to do because all you're doing is for the same model, you're just giving it more steps of reasoning as linguistic input, and you're getting it to produce the output. And you know, it does perform very well. Palm on its own, it doesn't do as well as GPT-3 on these sorts of, this is now arithmetic reasoning tasks, but Palm with chain of thought reasoning does better. Here's a really fun example, explaining a joke. So here's a very much of an inside joke. Did you see that Google just hired an eloquent whale for their TPU team? It showed them how to communicate between 2 different pods. That's maybe funny to Googlers. I'm not sure it's funny to everybody. But the interesting thing is that you prompt it with explanations of why a joke is funny, and then it tells you, it comes up with an explanation. TPUs are a type of computer chip that Google uses for deep learning. A pod is a group of TPUs. A pod is also a group of whales. The joke is that the whale is able to communicate between 2 groups of whales, but the speaker is pretending that the whale is able to communicate between 2 groups of TPUs. I mean, I think that's pretty good. Like, I'm not sure I could have explained it better than that. And sort of on a technical level, there was quite a lot of engineering that had to go into training, you know, these models on 2 TPU pods. You know, it was very hard work, right? And it took a big team, a lot of time, but then the efficiency that was obtained is pretty significant. So, you know, with 2 pods, 1.95 means that they were actually being pretty well utilized during this training. Okay, let me talk about LaMDA. LaMDA is a project that's looking at natural open-ended conversations. It was in the news recently, if you didn't see it. It's basically, LaMDA stands for Language Models for Dialogue Applications. It's based on a large language model with 137 billion parameters. That's actually not, you know, not among the largest language models out there. I mean, there are models that are much bigger than that. But it's trained on a lot of data that's a mix of dialogue data. So it sees a lot of dialogue between humans in its training data. And it's also trained on web documents. It's trained on code. So there is, like, you know, it's there are ways of kind of using that for interesting things. It's trained on Wikipedia as well, so that's where it gets a lot of knowledge from. And it's fine-tuned on human annotated data based on 5 criteria: safety, factuality, sensibleness, specificity, and interestingness. So it's trying to give interesting answers to questions. Because, you know, you can train a dialogue system that gives really boring answers. It's not very engaging. So here's just an example of, you know, dialogue. This is going to go by a little too quickly. Hi, I'd like to have a conversation demonstration for a blog post. Hi, and this is LaMDA replying. I'm a friendly and knowledgeable demonstration of the blog post. Okay, you know, this, I think this is going too fast to be able to follow. So the human is on this side, LaMDA is on that side. Sorry if I had to explain that. I guess that's a, you know, it's a sort of version of the Turing test, right? Now, you know, there are significant issues with taking something like LaMDA and releasing it as a product. So we're not there yet. We're not, you know, making a product out of LaMDA. We are thinking about how this sort of technology could be used in various different products. But, you know, what does it take to make these things safe? So pre-training data, you know, you want to pre-train data that's highly filtered. So you want to remove things like, you know, abusive language or biased language, you know, things that are like topics that are sort of unsafe to have in a data set. And unfortunately, a lot of conversations on the web are pretty unpleasant. So there's a lot of work that needs to get done to remove those things, and it's going to be imperfect, but it's not enough just to do that. That's just on the input data side. You also need some aggressive adversarial testing, testers that try to get the system to say unsafe things and flag them. And then, you know, that data, you can build discriminators that take the output of LaMDA in the context and try to figure out whether it's safe or not to use. And, you know, safety doesn't come from just making the models bigger. I mean, bigger actually helps, but, you know, you need to do a lot more to make these models safe. Misinformation is a really important aspect of these models. Like, you know, if you ask it, one of the problems with these dialogue systems and these language models is they want to answer. Or, I mean, I shouldn't personify, you know, I shouldn't anthropomorphize the models. The models don't want to do anything. They're just statistical representations of large data sets, right? But you give it an input, it'll produce an output, okay? And so if you ask it a question, it will give an answer, and the answer could be complete rubbish, but it'll sound very confident. Just like that person on Reddit that's going to say something really stupid and sound really confident, right? And so we need extra methods on top of these systems to avoid them producing misinformation. Or just like factuality, you know, we need systems that improve the factuality. And these are things that we measure and we try to optimize. So I could go on, I could talk about a bunch of things, but maybe we've been going for quite a long time. I'm going to flick through some of the other things just so you get a sense of other projects, but then I'll take some questions. Okay, so let me flick through things. It's not just language and images. We do a lot of work in the sciences as well. For example, annotating proteins. So you know of DeepMind's work on AlphaFold, that's on protein structure prediction from sequences, but some of the work that we've been doing is on function prediction, which is, you know, particularly useful as well. And this was collaboration with the European Bioinformatics Institute, which is close to Cambridge, the EBI, and essentially the use of machine learning allowed us to add about 10 years worth of functional annotations of proteins in one paper. So basically, this is over time, the number of proteins that have been annotated in the PFAM database, and machine learning really helps us automate the annotation of proteins. We work on the interface between language and robotics as well. So SEICAN is a system that leverages a large language model so that you can have a conversation with a robot. And it's kind of subtle because if you want to be able to control a robot with language, the robot needs to be able to take language and figure out what maps into its physical world and its action space. So, you know, if you say, how would you put an apple on the table? The large language model might give a bunch of answers, and then you rescore the answers in terms of things that seem like sensible actions for the robot to do, like pick up the apple. And then, you know, this is kind of the robot in action. I spilled my drink, can you help? And then I can help clean up the mess. I can bring you a sponge, and then, you know, etc. So it's sort of rescoring things. Okay. Neural scene representation. Let me skip over that. Basically, this is about three-dimensional representations of the visual world. JAX, I talked about a language framework, so we've been investing a lot in JAX. JAX is a framework for writing models and doing automatic differentiation and a lot of numerical computations. It's based on Python and NumPy, and very well tuned for GPU and TPU inference. So a lot of our work has been kind of built on JAX most recently. And a lot of models that you're probably aware of, like you know, Gopher, for example, was built on JAX. DeepMind uses JAX as well. But this is one of the things that we work in our systems and programming languages team. There's computational fluid dynamics simulations in JAX. You can use it for all sorts of numerical computations, not just for machine learning. BRAX is used for differentiable physics, which is super interesting. AlphaFold also is based on JAX. And it's open source, and it's something that has been growing in popularity. I'm going to skip over this and let me take some questions. Okay, so let me take some questions. And, yeah, great. I think you had your hand up. Yeah.
So my question is regarding LaMDA. So LaMDA is a dialogue system, but you also printed on 10% of the code. Like, what is the relation with the code and the dialogue?
Yeah. So yes, it's true. LaMDA is a dialogue system, but it's trained on a diverse data set. You can imagine dialogues about computer code. You can also imagine dialogues where your conversation might be, you know, to help you write a computer program. And so, you know, they threw in 10% computer code just for that reason. We also have Palm Coder, which is based on Palm, which is more significantly trained and fine-tuned on code. And that's actually really useful. Like these things end up being incredibly useful within Google. Like we have a lot of internal tools that try to leverage this just to help people deal with like really tedious parts of coding. For example, you know, helping with debugging, helping with commenting, helping with porting from one language to another. Some of these things are quite tedious. Okay.
Yeah, thanks for the talk. You talked about a lot of very interesting models that are all very large models. So actually, my question is not very technical. So personally, I have trained a very large model, which takes 2 months and depends on the device you use. So for the models with like about 540 billion parameters, it must take much longer time to train. So my first question would be, with the global shortage of chips and also the resource distribution difference between large big tech companies and academia, what do you think it would be the pros and cons of this resource distribution difference? And second, like big, large company like Google, what could this company do in order to make this distribution more uniform?
Yeah, no, this is a great question. I'll repeat the question. So the question is around the distribution of computational resources for training these large models, and big tech companies have a lot of resources to train these models. What are we doing to help with that? So one of the things is that we and many other companies are releasing some models, not all models, not always not always every model, because some of these models are very risky to release. If you release them, they could be used to, for example, I'm going to actually show you an example. This is, you know, I have a whole section to talk about our AI principles and responsible AI and potential harms, but you know, this is not with, this is using DALL-E Mini, not from Google, but you can see with DALL-E Mini, you can produce very biased images. So, you know, here it's an angry man. All of these images are of a black man, and images of violence, images of misinformation, you know, Obama with a gun, right? And, you know, this, like, you can produce these images. These are, DALL-E Mini produces very low quality images, but imagine if you produce high quality images, then that's even worse. So there are risks to releasing these models. However, having said that, we tend to push towards open sourcing and releasing models as much as possible. There are other companies that are doing this as well. Like, for example, Meta just released a very large language model. Hugging Face is releasing a lot of models. There are community projects that are trying to build and release these large models. And I think that's generally a good thing. We just need to be careful, right? Because there are recent examples of people massively misusing these models. Now, in terms of the compute resources, the way I tend to think of these is, yes, it's very expensive to train these models, but once you have a model, if you either have it available through an API or you release the weights of the model and somebody can actually run that, it's actually relatively cheap to run these things. And so the model itself becomes a resource that other people can use for very interesting follow-on ideas for research and so on. And that's one way of providing access. And we're actively looking at really good ways of doing that. Microsoft also does this. Microsoft has an academic program. Other companies are doing this as well. I think we all need to move in that direction. Yeah. Great.
Thank you for the talk. The premise of my question is the two talks. So your history from holistic machine learning and recent work on large-scale models, emergent phenomena, prompting, things like that.
Yeah.
What do you think is the role of formalism and theory versus intuition and engineering in AI research? And especially as I'm frustrated to see students, so just to hear it.
Yeah. So, yeah, so the question is about, like, putting the two parts of my talk together. What is the role of formalism in theory versus intuition and kind of large scale and things like that? Yeah, yeah. I mean, you know, at some level, I think some of the large model work is quite brute force. right? You just have a very large data set. You have to be clever. There's important things to do there to get it to work properly. And you have to understand the learning algorithms. You have to understand the optimization algorithms. You have to understand the parallel computation. There's a lot of research that goes into that, but it's not the sort of, it's not the formal research that I talked about before. There are other projects I didn't talk about where these two things come together. There is, in fact, a project on Dermacyst, which is actually using deep learning for dermatology use cases, where you point the camera at a sort of skin condition, and it gives you, some possibilities for what that skin condition might be. This is a great way to democratize health care and health predictions and diagnosis, but you really need uncertainty for that. So actually, the team at Google Brain that works a lot on uncertainty in deep learning, that has been using, probabilistic modeling approaches and so on, has been really key in that Dermacyst project, right? If you look at the diffusion models work, actually, like the team that did that really did understand probabilistic modeling. It's just kind of, under the surface there. So I think it's important to understand the foundations of the work, but it's also important to not get too obsessed with the formalism and the theory, and get your hands dirty on some practical applications. Yeah. Maybe I'll take one more talk, and then we have a bit of time for a break. I think. Oh, sorry, one more question or two. There was a hand up. Okay, go ahead.
Like a question about this denominator for safety of training data set. I think it's really very interesting to have a pre-processing step to train these models. So about the discriminator itself, how do you check it's not biased to specific classes?
So we have actually, this is there's a whole section of the talk which is on responsible AI tools. So we have a large team in Google Research working on tools that are used to evaluate whether models are responsible or not. And I'm going to just show you in the next slide some of these tools. So for example, model cards are used to sort of understand a model and represent some of the risks of a model. Data cards are used for data sets. We have something called the language interpretability tool, which is a way of probing a language model to understand, why it answered certain thing under certain circumstances. We have a tool called the fairness indicator, which looks at slicing and dicing models according to various fairness metrics. We have tools for looking at your data set. So Know Your Data is a tool that tries to evaluate bias in data sets and other aspects of data sets. It's adversarial testing, I mentioned that. So basically, you create a model, and then you need to have a team that is going to try to push it to do wrong things or bad things, right? And then use feedback on that. So this is why there's a big gap between training a model and actually developing, say, a product or a use case that you'd be willing to have, lots of people interact with. That's the hard work, really. There was a question in the back. Let me take one more. Yeah.
So I found it is an part quite interesting because for a few weeks, everyone thought that first study 2 and then the diffusion models are the way to go, and then party showed actually there's lots of ways. And this is quite interesting. But there's also a depressing takeaway from this. That sort of in the end, in machine learning research, we care a lot about developing clever methods and a lot of theory, a lot of intuition. But you're familiar, there's this idea of bitter lessons, and actually one way to look at machine learning research is just throwing more compute and large data sets at the problem makes it irrelevant what method you're actually using. It's not like a lot of things that we care about in research actually don't see the method as much. So how do you feel about that? Also, this parallel development, how's it internally at Google? Because like Party and Imogen, they both have sort of like building blocks that you could have provided, like the idea of the upscaling or partly create the language model portfolio, some data sets that you could have taken off the shelf and then add the layers to. So how's this like internally at Google?
Yeah. So the two questions are: is this kind of depressing to think that the bitter lesson is that you just need more data, more compute? For certain problems, that's still the lesson that we're getting, right? I think, you know, you're shining the light on problems where there's a vast amount of data, right? So this is text and images. Text and images are the two things you can get silly amounts of data on out there. When you look more broadly, there are many, many applications where you just can't throw more data and compute at things. And I think you know, I also think that the current state of machine learning is probably, you know, 1 or 2 orders of magnitude inefficient in terms of data and compute. And the cleverness is what's going to get us things like, you know, our human brains operate on whatever, less than 100 watts, right? And, you know, it's kind of a huge amount of headroom for doing things much better than we're doing. The second part of your question was around the kind of how does the internal dynamics work. We have a fairly bottom-up culture where different teams try different ideas, and then we try to encourage them to work together on bigger and better things. And so, you know, like right now, there's quite a lot of sharing between these teams. There was a joint blog post describing Imogen and Party, and we are looking at ways of combining these methods into newer and better methods. Great. All right, we're out of time now, I think. Great. Thank you.